Hello and welcome back. Today I want to continue looking at the topic of impedance matching by analyzing what needs to be done when the impedances that you are trying to match are complex. Last time I looked at how purely real or resistive impedances are matched using a lossless matching network built with inductors and capacitors, and today we will continue building on that, so be sure to check out the previous video before this one. That being said, let's begin. Now, in real life, most signal sources and loads will not be purely resistive. There will be some capacitive or inductive part, but in some cases, these effects are so small that they can simply be ignored. However, if the reactive part is non-negligible, you need to account for it. So when an impedance matching circuit is being designed, it needs to take into account not just the real resistive part, but also the imaginary reactive part of the impedance that's being matched. Now, this isn't as complicated as it may seem. That was a joke. But anyway, before moving forward, let's first remember a few things about impedance and how it is expressed as a complex number. So impedance, just like resistance, is a measure by which the flow of current is being opposed, but in AC. And what makes AC and impedance special compared to DC and resistance is that the voltage and the current are not always directly proportional. So even in AC, when you have a purely resistive load, the voltage and the current will be perfectly proportional. But when you have a reactive element, like a capacitor or an inductor, the voltage and the current will no longer be in phase. So you will get a phase shift. The capacitor will create a negative phase shift, the inductor will create a positive phase shift. And even though these two elements do not dissipate any power like the resistor does, so the capacitor and the inductor only store energy and then release it. So regardless, they still impact the flow of current through the circuit. And because we have these two different types of effects, they are expressed differently. So complex impedance is expressed as the sum of the real resistive part of impedance and the reactive imaginary part. And regarding this reactive part, if it's inductive, it's a positive value. If it's capacitive, it's a negative value. And this brings us to our first method to handle complex impedances. We can simply get rid of the imaginary part by resonating it away. So when you have multiple impedances in series or in parallel, the same rules apply as with resistance. So two impedances in series will be expressed as the sum of the individual impedances, and two impedances in parallel will be expressed by this calculation. Now, if the two impedances are a purely capacitive and a purely inductive reactance, the sum of them will be the difference between the two reactances, so the capacitive one is negative, and then the parallel equivalent will also be equal to this thing. And the importance of this is that if we have exactly the same capacitive reactance as inductive reactance, the two will cancel each other out, so the equivalent series impedance will be 0 and the equivalent parallel impedance will be infinite. So what this means is that in a circuit, if we can match the two reactances, they will cancel each other out and the circuit will behave as if none of them were there to begin with. So we can easily find out what the equivalent component is that will resonate with our reference component using the LC resonance equation. So by mixing around the terms a bit, we can easily work out what the resonant inductor will be, or the resonant capacitor, based on the reference component and the frequency of interest. And we can do all of this very easily using a spreadsheet. And to show off this effect, I prepared this LT-SPICE simulation. So first of all, we have our reference circuit. So we have a signal source, 1 volt, 1 megahertz sine wave, with a 50 ohm series impedance, and we have a 50 ohm matching load. So this will be our reference circuit. And to highlight the effect of the reactive elements, I created two new signal sources in which I also have once a parallel reactive element and once a series reactive element. So if we now run the simulation and check out the power that is delivered to the various loads, so with our reference circuit we're getting exactly a peak power of 5 milliwatts, and with the other two, so first of all with the parallel 1 nanofarad capacitor, we're getting slightly less, and with the series 1 nanofarad capacitor we're getting significantly less. So now let's see what's the effect when we add a matching reactance of different type. So I have the exact same circuits as before, so 50 ohms with the 1 nanofarad. But now I also added an inductor that has the same reactance as the capacitor at our frequency of interest. So only at 1 megahertz, the equivalent reactance of the 25.3 microhenry inductor is equal to the reactance of the 1 nanofarad capacitor. The two are of opposing sign, so they should cancel out. And if we check what happens, so again, looking at the power on the reference circuit, exactly 5 milliwatts. On our circuit with parallel 1 nanofarad capacitor and parallel inductor, we get the exact same thing. And on the circuit with the series elements, again, we get the exact same thing. So right at the beginning, the circuit takes a while to stabilize, but once it's stable, then we see that the matching reactances cancel out, and we're left with a stable system that behaves just like without the reactive elements. Now, adding extra components to your circuit is not something that you necessarily might want to do. So the next method by which we can handle complex impedances is to include them into the matching circuit. So to absorb the reactive part of the impedance that we're trying to match. Now, when designing a matching circuit, you can start by ignoring the reactive elements and only focus on the real resistive parts. So last time we've seen that if we want to match two loads, one that has 480 ohms, the other 50 at a frequency of 1 megahertz, we can use a series inductor of 23.3 microhenry and a parallel capacitor of 972 picofarads. The parallel capacitor being on the side of the largest impedance. But if our signal source and load already have some reactive elements, so for example our signal source has 100 picofarads of parallel capacitance and our load has, say, a series inductance of 10 microhenry, there's no point in trying to resonate these away. We can simply include them into our matching network by subtracting these values from the initial components. So instead of a 972 picofarad capacitor, we can only place an 872 picofarad capacitor and take advantage of the existing 100 picofarads in the signal source, and the same way with the series element, subtract the 10 microhenry we already have and only use 13.3 microhenry extra inductor. And of course, both these circuits will end up delivering the exact same amount of power to the load. Finally, we can combine the two methods if our load or signal source already has a reactive element, but of the opposing kind of what we would need. So for example, if we keep the same resistive elements, so 480 ohms and 50, but this time our signal source has a parallel inductance of 253 microhenry and the load has a series capacitance of 100 picofarads, we can handle these by resonance, so provide a matching reactive element that has the same reactance at our frequency of interest, and then take these extra elements and absorb them into our initial matching circuit. So by doing this, we end up having larger component values than we had before, but everything should cancel out. So if we now run the simulation, first of all look at the power dissipated in our initial circuit and compare this to what we get to our circuit with the various matching elements. Again, we can see that we get exactly the same amount of power being delivered. So the source and the load are matched. Now, there's one more case to discuss. What if you have a parallel reactance on the side of your lower resistance where you would need a series element, or the other way around, what if you have a series element on the side of the higher resistance where you would need a parallel element? What is the most efficient way to handle this case? So now, starting off from the same reference, so 480 ohms and 50 ohms, in the case that we have a series reactive element on the side of the highest resistance and a parallel reactive element on the side of the lowest resistance, we can compensate for these using resonance, so to provide an equivalent reactive element of the different type, so in series with the source and in parallel with the load. But now the problem is that we can't really integrate these into our existing matching network. So the circuit works, so if we compare the power delivered to the reference circuit and the power delivered to this circuit, they're exactly the same, but now our matching circuit has 4 reactive elements. Well, that's not good. And this is where things start to get a bit mathematical. At any given frequency, a complex series circuit has an equivalent parallel circuit, and vice versa, a parallel circuit has an equivalent series circuit. Point being that we can transform our circuit to be the kind of circuit that we need by calculating the equivalent values and designing the matching network as before, apply the resonance and absorption principles, and be done with it. How hard can it be? Now, I don't want to go into too many details with the mathematics behind this. I will link some sources in the description below, so go check those out if you're curious. But I'll just say that I put everything into a spreadsheet and let the computer do all the work for me. So, using these equations, we can figure out what the equivalent series circuit is for our parallel circuit. So for a 50 ohm resistor in parallel with 100 picofarads at 1 megahertz, we get 49.95 ohms and 101 nanofarads. And in a similar fashion, if we have 480 ohms in series with 253 microhenry, the equivalent parallel circuit is 5740 ohms in parallel with 276 microhenry. Now we can start from our previous circuit and plug in the various equivalents. So for the two series elements, we can put in the parallel elements. For the two parallel elements on the load, put in two series elements. And if we rerun the circuit, so just to check that everything's okay, we can see that exactly the same power gets delivered to the load. And similarly, if we look at the source power dissipation, so on the signal side in the upper circuit and in the lower circuit, again the same amount of power gets dissipated. So the two circuits are equivalent. But now, when we look into a bit more detail, well, having the two parallel elements in series with the signal source isn't that helpful, but having the two elements in series on the load side is helpful. So now we can start again from scratch with our matching network and provide a matching reactance to our initial signal source, and also provide a matching element to our equivalent load circuit. And this time, the two inductors can be united into a single component. Now we can see that we only need 200 something picohenry of inductance, so extremely small value, but this wasn't necessarily obvious when we had the 100 picofarads there. So now by combining the two inductors, we can create an equivalent 3-element circuit, and if we run the simulation and compare to our reference, we see that exactly the same amount of power gets delivered. So in certain cases, it might be helpful to figure out what your equivalent series circuit is or what your equivalent parallel circuit is. Now, as one of my patrons pointed out, there is a two-component solution to this problem. And it's relatively easy to figure out if you're using a Smith chart. But we're not doing that today. We're doing things the hard way. So let me show you another way of finding the two-component solution to this circuit. And this will require a bit of pen and paper. So the circuit that we will end up designing looks something like this. So we have our signal source with an input resistance and series inductor, and then we have our load with a parallel resistance and a parallel capacitor. And in between them we have a two-element matching network. Capacitor in parallel, inductor in series. Now, since our internal resistance is larger than our output resistance, we have a capacitor in parallel on the larger resistance side and then the inductor in series with the smaller resistance side. So we need to find an equivalent circuit with some intermediate resistance values that will make this thing work. We could try something like this where we have an intermediate virtual resistor, and to get this thing to work correctly, our virtual resistor, which is in parallel with the capacitor, should have a larger resistance value than our internal resistance, and on the other side, our output resistance is in parallel with the capacitor, so this thing should be the largest of the two, and well, this isn't really possible. You can't get these three equations to work at the same time, so this is not a solution. So we need to think a bit outside of the box and go for a triple stage impedance matching network that has two virtual resistors. And now with this sort of structure, so we have one matching network between Ri and Rv1, another one between Rv1 and Rv2, and the third one between Rv2 and the output resistance. So to get this thing to work correctly, we need Rv1 to be larger than our internal resistance, then we need Rv1 to be also larger than our second intermediate resistor, and finally we need our second intermediate resistor to be smaller than our output resistor. And now this is something that we can solve. There is a solution in which all of these terms as well as our initial condition are all met. So if we can figure out the various components for this network, then we can calculate our final matching network. So we can simplify this to our initial circuit by saying that our capacitor will be equal to the two capacitors in parallel, so the sum of them, and then our inductor will be equal to the two inductors in series. So again, the sum of them. So by simplifying this, we get back to our initial circuit. So now let's try and figure out what are the various component values. So first off, if we analyze our first circuit, we know from the previous video that we can calculate our matching components knowing the resistance values. So the formula for the inductor, for example, would look something like this. But in our case, we don't know our first virtual resistor value. We only know the input resistor and the inductor, and the frequency, of course. So we can turn the equation around a bit to calculate what our first virtual resistor value would be. And now if we punch in the numbers, this will give us a value for our first virtual resistor of 5744.2 ohms. And now that we know our series resistor, we know the virtual value, we can calculate the capacitor using the spreadsheet approach, and we can work out that C1 is equal to 91.8 picofarads. So first matching network is done. Let's move forward. We can now look at the last matching network, where again we know two of the terms, so we know the output capacitor and the resistor, and from here work out what our second virtual resistor would be. So based on the formulas from last time, this would be the relationship between the two resistors and the parallel capacitor. And again, if we turn things around a bit, we can work out that the resistor value in this case would be, and if we punch in the values, we get a resistor of 49.95 ohms. So now we have all of the intermediate resistor values, so the virtual resistor values, and knowing the first and second resistor value, we can now work out what the two components are. So again, using the spreadsheet, we can work out that the second capacitor will be 295.8 picofarads, and the second inductor will be 84.88 microhenry. So now we have all of the components, and we can finally figure out what our final components will be. So we will need a capacitor which is 387.6 picofarads, and we will need an inductor for which we also need the value of this L3. So from this virtual value we can also calculate the L3 value, which I skipped over, which will end up being 250 nanohenries. So adding this up with the other calculated value, we end up with a total inductor of 85.13 microhenry. So our final matching circuit, considering the various components, should look something like this. So now let's see if this actually works. So what I have here is the circuit that we've just calculated. So we kept our input and output complex impedances and we added the two new components. And if we run this thing and compare it to, say, our reference, so here we had about 500 and something microwatts, and with our new two-component circuit, we have the exact same amount. So this method works. So finally, let's try an experiment and apply these principles. For that, I prepared a tiny board with dual B and C connectors to which the various components will be attached. One side will be connected to a 50 ohm signal line and the other to a 75 ohm termination. And to perform the measurement, I will be using 10x oscilloscope probes, which will add some parallel capacitance that is not neglectable at the 50 MHz at which the measurement will be performed at. So I will try to measure the impedance of the signal source and the load, but also compensate the oscilloscope probe capacitance that's being added. So to start things off, I prepared a baseline measurement. So I'm generating a 50 MHz signal with an amplitude of 1 volt peak to peak. I'm injecting this into the measurement setup where I have a pass-through connector, and this is going into a 75 ohm load. I'm measuring the two ends using the oscilloscope, and on both channels I'm getting 1.12, 1.13 volts peak to peak. So the reason why we're not getting 1 volt peak to peak is because the impedance that our generator requested, 50 ohms, is not being delivered. So we have 75 ohms. So that's why we're getting a higher voltage. So now let's try to improve on this by adding our matching circuit. So to start things off, I put the initial matching network that we should be using based solely on the input and the output impedance. So I have an 110 nanohenry fixed value inductor, and I have a 32 picofarad capacitor, so 22 picofarad in parallel with a 10 picofarad. So this was the closest that I could get to the 30 that the calculations were telling us. And if we now look at the measurement, well, on the input we have 890 900 millivolts, so substantially lower than the 1 volt that we should be getting. And on the output we have 1.17, 1.18 volts peak to peak. So it's close to what we should be getting, but we still have a problem on the input side. So now let's slowly try to add in the matching components to compensate for the capacitances that our probes are bringing. Now, regarding the properties of my oscilloscope probes, I found this catalog online, and the probe that I have is the PP215, and this has an input capacitance in 10x mode between 16 and 20 picofarads, but I tried to measure it and it was a bit lower than this. So in the experiments I will be using the value that gave the best results, which is a bit smaller than these values. So now I decreased the capacitor a bit to compensate for the capacitance present in the second probe, and we have some better values. So on the input we have 980, 990 millivolts, and on the output we have a peak-to-peak voltage of about 1.19. So we're getting much closer to the ideal values. And now I only left the 22 picofarads on the output, and I added the 660 nanohenry inductor on the input side, so to compensate for the input side probe. And finally we have some very good measurement values. So my input probe channel 1 is measuring 1.01 volts peak to peak, almost exactly the 1 volt that we should be getting, and my output is measuring 1.18 volts peak to peak on the 75 ohm load. So it's not really the 1.195 that we're supposed to be getting, but we're extremely close. So with all of the matching components in place, we have an almost ideal situation, with some losses occurring, of course, but much closer than what we started off with. In the end, handling complex impedances is not that difficult if you apply the two principles discussed today, resonance and absorption. Your impedance matching circuit might end up having a few more components than before, but this way at least you will have a proper impedance match at a specific frequency. And with that said, hope you got some useful information out of this. Leave your thoughts in the comments, thank you for watching, make sure to subscribe to be up to date with all my videos, and see you next time. Bye bye.